Alrighty, so this is gonna be Physics 111, Chapter 4, which is gonna be motion in 2 or 3 dimensions. So let's go ahead, come into our chapter 4 over here. Now, a position vector locates a point in space. So extends from a reference point to the particle. The position vector is going to equal x in the I direction, y in the j direction, and z in the k direction. So your r is going to equal x in the I direction plus y in the j direction plus z in the k direction. So let's say, for example, we have the reference point minus 3, 2, and 5. That means our position vector is going to be minus 3 in the I direction plus 2 in the j direction plus 5 in the k direction. Now, looking at the position vector, that means, let's say you have our first position vector. So let's say R1. R1 is going to equal to, I don't know, x, whatever x1 is in the I direction. Plus y1 in the j direction plus z1 in the k direction. Let's take another position vector, I don't know, R2, which is, again, x2 in the I direction plus r2 in the j direction plus z2 in the k direction. Now, remember we defined delta before as the difference if you have delta x, or the position of delta is going to be your final minus your initial, x2 minus x1, or x final minus x initial. So let's do delta of our position r that we have right now. So this is going to equal to what? Your second vector minus r1. So let me actually define this. So this is your displacement. Which is your what? Change in position. So your displacement on this one be R2 minus R1. Let's go ahead and fill in the blank on this one. So delta R is going to equal to your x2 minus x1 in the I direction plus y2 minus y1 in the j direction plus z2 minus z1 in the k direction. Well, if you notice, oh, we have x2 minus x1, which is going to be what, delta x, y2 minus 1, which is going to be what, delta y, z2 minus z1, which is going to be delta z. So your displacement for the r vector is going to equal your delta x in the I direction plus your delta y in the j direction plus your delta z in the k direction. Now we defined, let me go ahead, the velocity, which is v average, that's the average velocity, is, well, actually, let me just go ahead. Let's do this. The velocity as distance over time. Okay. In our case, is that r vector, that's our distance, divided by your time. So for your average velocity, what you're gonna have? You're gonna have the displacement delta r divided by your time. So let me go ahead and do this. So delta r, we can go ahead and substitute this little fella with delta r. So what do we get? You get delta x in the I direction plus delta y in the j direction plus delta z in the k direction. That's all divided by delta t. Oh, I forget the delta. The average velocity is delta v, delta r over delta t. So this will make your average velocity as your delta x over your delta t in the I direction plus delta y over delta t in the j direction plus your delta z over your delta t in the k direction. So let's do an example, shall we? Let's say a particle goes 12 meters in the I direction plus 3 meters in the k direction and 2 seconds. Find the average velocity. That means your average velocity in this case is going to be your delta r over delta t, which in this case would be 12 in the I direction. I'm like writing units, so I'm actually working on this, so I'm just going to skip the units for now. 3 in the k direction divided by 2, which is going to be your 12 divided by 2, 6 in the 6 meters in the I direction, plus 3 over 2, which is 1.5 in the k direction. So it's going to equal to 6 meters in the I direction plus 1.5 meters in the k direction. Wonderful. So we're talking about the velocity, right? And how is the velocity is your average velocity, say delta r over delta t. That means your velocity actually as the time goes from whatever it is to 0 for the limit, what you're gonna have? You're gonna have your dr with respect to time, dt. Well, again, we defined r. Let me go ahead and get this. We defined r as x in the I direction plus y in the j direction plus k in the plus z in the k direction. This is supposed to be an I. That means your velocity is going to equal to d for x in the I direction plus y in the j direction plus z in the k direction divided by, with respect to t, dt. I mean, this is going to equal to dx over x, dx over dt in the I direction plus dy over dt in the j direction plus dz over dt in the k direction. So we define the velocity as your point vector r over t, which r is, you got your x direction, your I direction, your j direction, your k direction. That means your dx over your dt, that means that's your distance over your time. Your distance in the x direction divided by t, distance of the y direction divided by t, distance in the z direction divided by t. That means, let me go back over here in red. This little fellow over here, that's going to be your, actually, that's a little thick. That's your Vx. This is your Vy, your velocity in the y direction. This is your z, your velocity in your z direction. That means your velocity is going to equal to, your velocity, go ahead and make it a vector. Your velocity is going to equal to, your Vx in the I direction plus your Vy in the j direction plus your Vz in the k direction. And again, given that, let me actually go ahead and write this down. Given that dx is going to equal to dx over dt, dy is going to equal to dy over, this is the y direction over dt, and dz, again, that's your dz over your dt. So that's for the velocity. Now, with the velocity come with the acceleration. When we talked about the acceleration, again, same thing. We said the average of the acceleration was your velocity over your time. That means your average acceleration is your change in velocity over your change of time, which means is your v2 minus your v1 divided by your delta t. You go ahead and label these out real fast. Again, your dv over your dt, or you can say your average velocity, sorry, your average acceleration is your change in velocity with respect to time. That means, again, we're going to define your velocity vector as your vx in the I direction plus the velocity in the y in the j direction plus the velocity z in the k direction. I mean, this one's going to equal to dvx over dt let me just go ahead dt and open up vx in the I direction plus vy in the j direction plus vz in the k direction. Which, let's just go ahead and break it out. What you're going to have dvx over dt in the I direction plus dvy over dt in the j direction plus dvz over dt in the k direction. Well, again, we define the acceleration as your velocity over your time. That means, actually, let me go ahead and write this down in a different color. We define the acceleration as your velocity over your time. So basically, we got your dvx over your dt, that's your acceleration in the x direction, that's your acceleration in the y direction, dvz over dt, that's your acceleration in the z direction. Your acceleration in the x direction, go ahead and write it down, dvx over dt your acceleration in the y direction, dy, dy, it's not y, I'm sorry. It's y direction equals the velocity in the y direction divided by dt, and the acceleration in the z direction is your velocity in the z direction divided by dt. And this is going to be your acceleration for your x, for your x direction, y direction, and your z direction. Now, going back to chapter 2 or chapter 3, when we talked about vectors. So let's say you have a velocity vector going in this way. Let's call this v naught. So this is actually giving me a convolution of your x-axis, your velocity in the x-axis, and the x direction, your velocity in the y direction. So this is going to be your v naught in the x direction, your v naught in the y direction. Now, your initial velocity, what is that going to equal to again? Let's say your v naught is a convolution of your v naught x in the I direction plus v naught y in the j direction. Now, over here we got an angle theta in the triangle. Angle theta. This angle theta, this cosine, that angle theta is going to equal to your x-axis, your adjacent, your next to it divided by hypotenuse. So your x divided by hypotenuse, which is going to be in our case your v naught x divided by your v naught. Your sine the angle, which is going to be your y over your h, is going to be v naught y divided by your v naught. This means that v naught in the x direction is going to equal to your velocity v naught cosine the angle, and for this one, your v naught in the y direction is going to be v naught sine the angle. Now, if you remember from our chapter 2 chemical equations, we had an equation that said your distance was your Vt plus At squared over 2. So let's say we look at for the distance, let's say you look at the displacement in the x direction. So if we look at the horizontal motion, our displacement in the x direction, let me actually go ahead and write this down. So let's do this one for horizontal motion, which is going to be in the x direction. That means our displacement delta x is going to equal to v naught x multiplied by t plus at squared over 2. Well, on the horizontal motion, we will have no acceleration. Let me go ahead and just write this down. Let's say you have no acceleration. That means your acceleration is equal to 0. That means this whole thing is going to equal to 0 anyway. So, which means that your delta x is going to equal to v naught x t plus 0. So your delta x is going to equal to v naught x t. But we define v naught x as v naught cosine theta. Let me go ahead and write this down. We defined v naught x as v naught cosine theta. Let's go ahead and substitute. Actually, let me stay on red for this one for a second. Actually, we green. So we can substitute this fella over here. So what you're gonna have is your delta x equals your v naught cosine theta multiplied by t. And let's call this, let me get a different color. Let's call this equation 1. Okay? Go ahead and do that. All right. Now that's for horizontal. Now let's look at the vertical motion. So let me actually get a new one. So let me actually look at the vertical this time. That means your delta y, and let me go ahead and write this down. Your distance is v initial t plus at squared over 2. That means your delta y in this case, because we're going in the vertical, so we're going the y-axis, is going to equal your v naught in the y direction t minus at squared over 2. Now, the acceleration when you're going in the vertical motion is going to equal negative gravity. You're going down there. So it's just going to be opposite of the gravity. So your delta y is going to equal to v naught yt minus g. So minus and plus and negative is going to be a negative anyway. So let's just leave it at a negative t squared over 2. Which is going to equal to v naught sine theta t minus gt squared over 2. And let's call this equation 2. Oh, by the way, I went ahead and forgot to write this down, but let me just go ahead. From before, v naught y equals v naught sine theta. And again, we got this from our little equation, v naught y equals v naught sine theta. All right, yeah, so that's your delta y. Let me just forget delta y. Delta y equals v naught sine theta t minus gt squared over 2. Now, you also, if you actually remember from chapter 2, one of the equations that we had was your v final, or I'm just going to say v equals your initial velocity plus at. Actually, it's not your time. And in this case, your v in the y direction, because we're talking about vertical motion. Your v in the y direction final is going to equal your initial velocity in the y direction, which is going to be v naught sine theta minus gt. Again, your acceleration is your gravity. Let me go ahead and write this down. So your vy equals your v naught sine theta minus gt. Let's call that equation 3. That means your v squared in the y direction is going to equal to your v naught sine theta squared minus 2 minus 2g and your y minus y naught. Now, let me go ahead and get a new page over here. So we said that your delta x, which is going to be your v naught cosine theta for t, we said that equation 1. And we said the equation 2 was your delta y equals v naught sine theta for t minus gt squared over 2. That's equation 2. Now, let's take equation 1 and solve it for t. So solve equation 1 for the time t. That means, go ahead and write this down. Your time is going to equal to your displacement delta x divided by v naught cosine theta. This is still equation 1. We just rearranged it. Now we're going to sub equation 1 into equation 2. So we're going to take this little fellow over here and we're going to substitute him on this one. So what we're going to get? Let me go ahead and write this down. Delta y equals your v naught sine theta t minus gt squared over 2. So that means your delta y is going to equal your v naught sine theta. Again, instead of t, we're going to put delta x over v naught cosine theta minus g delta x squared divided by, that's square, so this would be, we get the 2 v naught cosine square theta. Let me go ahead and open it up. Usually delta y is going to equal to your v naught sine theta delta x divided by your v naught cosine theta delta x minus g delta x squared divided by 2 v naught squared cosine theta squared. Well, we have a little coincidence. Your v naughts over here cancel out. And then we have your cosine on top of your sine, which is going to be your tan theta. So really the displacement in the y direction is going to equal to your tan theta delta x minus g delta x squared divided by 2. I'm just going to write that v naught cosine theta squared. And this, ladies and gentlemen, what we call your equation for projectile path. Now, so we said that your delta x which is your v naught cosine theta multiplied by your time. Now, we're talking about horizontal range, so we're gonna say that your delta x, that's gonna be r, which is gonna be your horizontal range. Horizontal range. That means your r, I'm just gonna write it in terms of r right now, your range that is gonna go is v naught cosine theta multiplied by t. Now, When we're talking about the range where your delta x equals r, that means your y direction, or your vertical direction is gonna equal to 0. Okay? That means, let me go ahead. Wait, remember our little equation, dy equals v naught sine theta t minus gt squared over 2. But we said that delta y and there is going to equal to 0. Talking about horizontal range. So that means your 0 is going to equal to your v naught sine theta for t minus gt squared over 2. That means your v naught sine theta t is going to equal to gt squared over 2. We move that to the other side. Divide both of them by t. So what you got? V naught sine. Let me go ahead and put this down. V naught sine theta, divide both of them by t equals gt over 2. That means the time is going to equal to 2 multiplied by v naught sine theta divided by your acceleration of gravity, g. Well, we can actually use this time because we're talking about horizontal, and we can actually substitute it in this little fella right over here. So where your delta x, again, let me go ahead and write this down. Where your delta x equals v naught cosine theta multiplied by t. And again, let me go ahead and substitute this one over here. So that means your range, and again, we said x is your range. That means your range is going to equal to v naught cosine theta. And we said it's going to be step t to v naught sine theta divided by your gravity g. Oh, so what happens? We got 2 v naught, so this is going to equal to 2 v naught squared sine theta cosine theta divided by g, the gravity. Now, we actually, if you remember from our trig class, we had a little identity for these two, right? What was it? Sine 2 theta is going to equal sine theta 2 sine theta cosine theta. So 2 sine cosine equals 2 sine 2 angle. So that means our range would be v naught squared sine 2 theta divided by your gravity. Now, your maximum horizontal range is at 45 degrees. And we actually seen that before. We had a little video. I'm gonna go ahead and show it right now real fast to show about the 45-degree angle. So in this one, again, you want to find the horizontal distance. So we want to see what angle that goes in maximum distance. And again, we've seen this in chapter 2, but I think it's very important to see it again. So we can go ahead back over here. So as you see, it was 45-degree angle. That's the maximum range, horizontal range. If you want to go throw something at the maximum amount. Now, let's say you got, I don't know, you have something that's connected that's going in a circle. I don't know, kind of like a drone or something that's going in a circle. Let's say this. Let's go over here from the middle, right? So you got a drone, so this one going in a velocity this way. When it's right over here, it would go in a different velocity. So let's say that's your v at time t equals 0, or t naught initial time. And then let's say you got the object. Go ahead and just give a different color on this. You got an object over here, again, that's going in at a velocity. It's going in a circle, right? And this velocity is at time e final t. So you say this is your initial position, that's your final position over here. Now, because it's going in a circle, what are you doing? You're creating an angle that's going in. So let's say if this was phi, and let's call this is beta, and let's say call this is alpha. According to the laws of triangles, your alpha plus beta over here, that has to equal to 90 degrees. So your alpha plus beta, that's equal to 90 degrees. And your alpha, if you continue the triangle, your alpha, according to the laws of triangle, all three of them has to be 180. So this is going to be 90. So your alpha plus theta is going to also equal to 90 degrees. And if, let's say you subtract those up, right? Let's say you subtract those, alpha minus alpha is 0. So what you get? You get beta minus alpha minus theta equals 0. That means your beta angle is going to have to equal to your theta angle. So these two angles equal. Now, the velocity that's actually is traveling, the velocity that is going, which is going to be your distance over your time. Your distance is going to be your circle, the diameter of the circle, so it'd be your 2 pi r divided by your time, t. So let's say so let me go ahead and draw this one over here. So if you actually compare the triangles that I'm drawing over here, right? So you get this triangle over here that's going in a circle. So in a normal circumstance, here this. So what do you have? You have your velocity. Let's say you got the first one, velocity at time t naught. And this one we got, when you go in, you got your velocity at time t. And of course, between them, you got your displacement of the velocity. Now comparing it to what we have, which is, again, this is gonna be your r, your radius. go ahead. So this is actually, and let me go ahead and do this. Yeah, see, it's going in a curved path. Now this curved path is going to be your distance. And again, your velocity is your distance over your time. That means your distance is your velocity multiplied by your time. So this is actually your velocity multiplied by your change. Well, we have T1 and T0. So the velocity multiplied by a change in time. And again, this is R for your radiuses that's going in. So if you do the, well, let me actually draw this a little better. This just looks a little better. So you got R, and this is V delta T that's going in. And here's your angle theta that we have. Let me go ahead and put that angle theta. You can see it's according to the law of triangles. So your delta V over one of them, delta V over your velocity is going to equal your VDT. Actually, let me write it in red so you know which one it came from. So let me do the first one red. So your delta V over your V is going to equal to your V delta T divided by your radius. That means let's go rearrange it. Delta V over your delta T is going to equal your V squared over R. Now again, if you notice, let me actually get blue. These two, that's going to be your centripetal acceleration, or your acceleration, I'm sorry. So centripetal acceleration is going to equal to V squared over your radius. So I think we have a question in there about this. The bobsled track contains the turns and radius of 33 and 24 meters times the centripetal acceleration, each of the speed of 34 meters per second, with the answer multiples of g. Actually, let me go ahead and write this one down, centripetal acceleration. Let's do this example. So your R1 is 33 meters, and your R2 is 24, and your speed is 34. R2 is 24 meters, and your speed is 34 meters per second, where your gravity is 9.8 meters per second squared. And you want to find the centripetal acceleration one for the first one, centripetal acceleration for the second one. And you know that we said the centripetal acceleration is going to equal to your V squared over R. That means AC1 is going to equal to your 34 squared divided by 33. This is going to equal to 35 meters per second squared divided by 10. So what you get, like almost 3.6 G or 3.5 G. AC2 is going to equal to, again, to your 34. Get a little space, 34 squared divided by 24. So that's going to equal to 48 meters per second squared. The 48, that's almost at what, 4.9 times the gravity that you are going at. And that should conclude chapter 4 for Physics 111. If you have any questions, just email at abu and aem@uah.edu, or you can give me a call at 256-348-1480. Thank you.